Hello everyone, my name is Ravi Gummaluri. I work for Micron Technology. I'm part of a system architecture team. Today I'm going to talk about memory expansion with CXL ready systems and devices. Anil and Simek have touched upon how important it is, the memory vendor to enable the ecosystem. I'll talk about how we are working with various ecosystem partners and enabling various CXL solutions here. Before I talk about CXL expansion memory and solutions, I would like to touch upon the memory demand and scaling challenges and how CXL memory expansion is solving those challenges. I'll specifically talk about capacity expansion solutions, how database applications are getting benefited out of it, and there are bandwidth expansion solutions, AI and HPC workloads, how they can benefit out of it, and finally conclusions and next steps. So we all know there is a huge demand for memory, especially for data center applications. It's 26% year-over-year increase, but we expect that it will scale with AI applications. And the second figure shows that CPU performance and memory performance. Memory performance is not really able to scale with CPU performance. Memory latencies are improving around 1.1 times every 2 years, but processor speeds are doubling every 2 years. So there is a huge gap between memory performance and CPU performance. And at the third figure, we see that memory capacity per core is not really able to scale with the core count increase. And if you see, the memory is 50% of overall server cost. So how do we solve the increased memory bandwidth, capacity requirements, and reduce the TCO? So CXL memory expansion is one of the solution, but it is the best solution today, where you can solve bandwidth expansion, capacity expansion, and solve the TCO problem. So if you see in the right-hand side, the memory paradigm or the memory hierarchy here, there is a huge gap between main memory and SSDs. CXL is going to fill this gap with various solutions that we have today. And CXL expansion cards are basically a cache line granular, and they are CPU-less NUMA nodes. They're hot pluggable memory. This is the major advantage, where with the main memory, if the DIMMs are down, you need to reboot the machine in order to plug out, where there is no hot plug support. But with CMMs, what we have today, they're hot pluggable memory, and you can replace them without shutting down the server. So this is one of the major drawback what main memory has, and it is being solved by CXL. And CXL comes with various form factors. Today we have E1.S, E3.S, and future we will have E5.S, and we have add-on cards. So it supports various form factors today. And it can be interoperable with various memory types like DDR4, DDR5. Like Anil said earlier, you can have a DDR5 on the host with RDIMMs, and you can have CXL module with DDR4 behind CXL, and they can do interop between both of them. So this enables us with various media types can be behind CXL, and it can work with the CXL host. The major applications for CXL expansion memory are like the capacity expansion. It's a no-brainer, like we are adding more capacity to the system by adding a CXL card to the system. When we attach a CXL memory module to the system, it enables as a second tier memory, and it exposes to the operating system as another tier to the system. Now, how this tier is being exposed to the applications and OS is dependent on the solutions that you're looking at. In a capacity expansion solution, this second tier can be exposed as an app transparent, meaning app doesn't know whether there is how many tiers are there, whether a CXL memory, another tier is being attached. It just knows that it should require to allocate a memory, but it is the OS or the user libraries which takes care of this allocations by having multiple tiers in the system. So apps are not required to modify, or it doesn't require to be aware of how many tiers in the system. They can run as it is and just ask for memory. In an application managed way, the applications are aware how many tiers are there in the system, and then they can allocate a particular memory allocation in a given node. Example are libnumas. You can use libnumas to ask for a particular NUMA node you want to allocate a memory. And further applications can be modified or optimized in order to make use of various tiers in the system. One of the example is libmimkind. This library can be used by applications in order to make use of various tiers in the system. When we have a CXL switch and a fabric manager, fabric attached memory, then we are adding another tier to the system. This will have higher latencies, but you are adding more capacity to the systems. By CXL switch, you can scale the number of CXL modules that you can connect to the system and have a higher capacity to the system. So this is one of the major use cases of the CXL memory expansion, where capacity expansion use cases are very important. The second important use case is CXL memory bandwidth expansion. We need to interleave between the DDR, local DDR, and the CXL in order to achieve higher system bandwidth. There are various ways today that we can do for interleaving between DDR and CXL. There is a hardware-based interleave, there is a software plus hardware-based interleave, and there is software-based NUMA interleave. I'll talk about these interleaving solutions in the next slides. So we did with the CXL ready platforms and our Micron CZ120 module. In this example, we have connected our CZ120 modules to AMD Bergamo, where it has 128 cores and it has 12 memory channels on the host platform for each socket with DDR5 supporting DDR5. Overall, you can see that 768 GB of capacity can be added to the system. And what we are plugging in is we are plugging 4 CXL modules, Micron CZ120 modules. This is giving a capacity expansion. And you can see the system capacity has increased by 135%. Micron CZ120 CMM module is a CXL 2.0 spec compliant. It's a PCIe Gen 5 by 8. It has various features. It has a low latency, RAS security features we have. And we have two DDR4 channels behind the CXL module. So in this system configuration, we have tried various workloads and analyzed how CXL memory expansion is giving a overall system performance. And then one of the example that what we have analyzed is TPCH. So this workload, basically we have run a 3 TB of data set with the 3000 scale. We have enabled on the local DRAM versus the DRAM plus CXL solution. And we have analyzed what are the bottlenecks that we have today with the workload and how CXL memory is solving those bottlenecks. So if you see on the left-hand side, if we are running the TPCH workload, which is a 3 TB database with 3000 scale, that database, when we run on a only DRAM, which is fully populated with 12 channel DDRs with 64 gig RDIMMs, we can see that it's performing around the number of threads. As you see the number of streams, if you scale, the performance of the local DRAM fully populated versus the DRAM plus CXL modules, we have connected 4 CXL modules. With this, you're increasing the system capacity to 1.768 GB. With this increased memory, what we have observed is for a single stream TPCH workload, we see 23% benefit. For 8 streams, we see 96% benefit in the performance. And for 20 streams, we can see around 300 plus performance here. And on the right-hand side, if you see, there are various graphs with CXL and 64 gig RDIMM with 96 gig RDIMM, how CXL is actually compared when we scale the capacity from 64 gig to 96 gig in the RDIMM's 12 channel RDIMM. Still, the performance of CXL is giving you 1.66 times better than the 96 gig RDIMM on the host. So clearly, we can see that there is a performance boost with adding additional capacity to the system. And we analyzed further why we see the performance benefit with CXL additional capacity is, if we don't have a CXL memory today, there are lots of IO stalls because the local DRAM channel capacity is not enough. It has to go to the SSDs, and there are lots of IO transactions with the higher latencies and page out, page in. We see a lot of IO stalls happening, and that is the major point for degrading the performance. When we add CXL memory to the system, we are adding additional capacity and memory to the system. It is reducing the IO stalls. It is reducing the data movement between SSDs and memory. This is bringing down the IO stalls, and that is improving the performance here. So on an overall, CXL can provide better performance for capacity-intensive workloads. Coming to the second use case with CXL, when we talked about CXL use cases, we talked about capacity expansion. The second one is bandwidth expansion. For bandwidth expansion, we have to interleave between the DRAM plus the CXL memory. So there are various ways. One of the ways, hardware heterogeneous interleave, where your system address map is chunked and it is a flat memory model, and the system address map is chunked between your local DRAM and CXL. DRAM can be 8 or 12 channel DDR, and an example is 4 channels. If you 4 CXL modules you're connecting, then the whole system address space is chunked between local DRAM and CXL. This is easy to configure at the BIOS time, but it has lots of cons here. Its example is kernel cannot manage this memory allocations because it is chunked. The system address map is flat. The kernel cannot manage this, and it hides the NUMA topology from the OS. So the applications cannot have a flexibility to ask for allocations on particular nodes. It's a fixed configuration where application wants to vary any configurations, it cannot vary. Applications can be sensitive to various parameters like latency, bandwidth, and capacity, but this is a fixed configuration and we cannot tune those applications. And the major other drawback from this heterogeneous interleave hardware is the CMM capacity to be ISO capacity with the DRAM. Meaning, if you have a 64 RDIMM on your module, on your host, your module also need to be ISO capacity with it, meaning your CMM also need to be 64 gig capacity, because you're interleaving the system address between DRAM and CXL. So having a higher capacity on the CXL cannot get benefited out of this. You have to be ISO capacity with your RDIMMs. So this restricts the capacity on the CXL, and some of the capacity expansion use cases cannot really benefit out of this. The other way to achieve the interleaving between local DRAM and the CXL is a hardware plus software based interleaving. A subNUMA clustering can be formed in the host, meaning you have a 12-channel DDR. When it connected to AMD EPYC here, you can subdivide these 12 channels into subNUMA clusters, where each cluster can handle 3 RDIMMs. And you have 4 NUMA nodes you have created. Instead of 12-channel 1 NUMA node, we are dividing that into a 4-channel NUMA nodes. And you have CXL, 4 CXL cards connected as 1 NUMA node. So instead of 2 NUMA nodes, local 1 and CXL, we have divided the local into 4 NUMA subclusters and created 4 NUMA nodes and 1 CXL attached to the system. Now we can interleave with NUMA CTL and software tools that we have today. We can interleave the page allocations between these 5 NUMA nodes. Because local NUMA nodes are being split from 1 to 4, you have a better performance on the system, and CXL attaches for the once you have a cold pages that can be really used from the CXL point of view. So in this mode, the NUMA topology is enabled. The earlier hardware heterogeneous interleaving, the OS is not able to control the page allocations. There is no NUMA topology. And here in this topology, you are enabling NUMA topology. Kernel has managed the memory. It overcomes the capacity limitations imposed by hardware interleaving solution. The cons is, again, it is a fixed configuration here. Once you configure this at the boot up time, you cannot change the number of NUMA clusters, and you cannot really tune each application for this workload. So the other way for interleaving between the local DRAM and CXL is a software way, where if the application wants the 100 pages to be allocated, you can have a flexibility that you can ask that 80 pages can be allocated in node 0, and you can ask for application to allocate 20 pages from node 1. So you can interleave in various ratios between local and DRAM. This interleaving gives a benefit to the overall bandwidth of the system. And this is scalable. It's not a fixed configuration. According to the application, if you have various read-write ratios in the applications, according to your ratio, you can tune your page allocations in the system. So this is NUMA topology enabled. OS can handle it and overcomes the capacity limitations imposed by hardware interleave. And this is another flexible configuration, like in your software plus hardware configuration we discussed earlier, has a limitation of fixed configuration. Here, we don't require to have a fixed configuration. It can be scalable. According to the application needs, you can scale the interleave between local and the CXL. The major cons is it is applicable to direct attach today. But as you see, when you have a switch and fabric attached memory, this kind of interleavings is very difficult to manage. But there is a lot of work which is happening on the consortium. Even we are working with these kernel patches. We are trying to publish along with Memverge and other partners in the industry. And Micron is driving towards a solution, software interleaving solutions for overall bandwidth improvement of the system. So with the software interleaving solutions that what we have today, we try to analyze a AI workload, which is Llama inference workload. Here on the left-hand side, you can see the system configuration. Earlier, I have showed on the AMD Bergamo how we have analyzed the capacity expansion TPCH workload. In this example, I'm taking the Intel Xeon platform where we have 8 channels local DDR5 running at 5600, and we have 6 Micron cards which are connected to Intel Xeon platform. On this system configuration, when we run an MLC workload, by varying the read percentages in the MLC workload, we can see the system performance improving to 25% and 100% read workload. And when we come to a 60-30 or 60-40, by interleaving DDR plus local at a 70-30 or 65-35, we can see almost a 45% improvement in system bandwidth. So this example tells us, like, by varying various read-write ratios, you can see a sweet spot which is coming between 70-30, 65-35 according to the application needs. So if my application is a 70-30 workload where I have 70% reads and 30% writes, I can choose a sweet spot where it might be around 65-35, meaning 65 I can choose pages to allocate on DRAM and 35 on CXL. That gives an additional bandwidth of 45% to the overall system. On the below, we have run the same application on a real workload Llama, and we do see that it is improving 22% when compared with the running on the local, complete, fully populated local DRAM. And the number of tokens outputs are also improving. So this proves that, like, by interleaving between the DRAM and local in a software way, you have a tunability in the system, as well as it is improving the overall system bandwidth. And a lot of applications like AI applications, which are sensitive to bandwidth, really get benefited out of this bandwidth expansion use cases. So I'm just coming to the conclusion that before we started the discussion, the memory expansion can provide solutions to increased memory bandwidth and capacity requirements. We have seen that software interleaving between DRAM and local is actually giving a better performance to the overall system, and it is getting benefited by AI and HPC workloads. And similarly, we have seen the capacity expansion where the database and data analytic applications are really benefiting out of this memory capacity expansion. For the next steps, I think we have understood that without changing the applications today, we are able to benefit the capacity expansion and bandwidth expansion. But their applications can be further tuned or optimized to know various tiers in the system, and page allocation algorithms can be developed around it to improve or boost the performance further. And it can also take advantage of various media characteristics. Today, we are not exposing what is the media characteristics to the application to take advantage of it. It can be further enhanced with those media characteristics and memory tiers. In the CXL memory pooling and fabric attached memory, we can help further in defining various memory tiers to reduce system TCO. So in a given CXL Ready 2.0 platforms today with Micron CZ120, we have analyzed the benefit of memory expansion, bandwidth expansion, and TCO, overall system TCO. I'll just touch upon the introducing Micron CZ120 memory module, which is delivering capacity, bandwidth, and flexibility. This comes in two SKUs, 128 GB and 256 GB. It can increase the capacity of overall system up to 2 TB. The bandwidth is 36 Gbps for a 2:1 read-write combination, and it comes in E3.S2T form factor with the BI8 in the front end. This is an industry standard form factor for broad deployment. So, any questions for me?